we are carrying on with this paper, question 4 of 18th of November 2017 electrical theory. So our question to start with is from the nameplate, calculate the output power of the motor in kilowatts. So we look, well, the kilowatt area is empty, but we have the horsepower. Horsepower is rated for output, not for input. They're asking for our output power. So it's a simple matter of 30 times 746 equals, and we will get, if we pull out our calculator, 746 times by 30, and we get 22380 watts. Now, they asked for kilowatts, so now that becomes 22.38 kilowatts, and that is our output. Base to right output, but if we look at our model answer sheet, it says horsepower times 746, 30 times 746, so 22.38 kilowatts. Now they want us to generate our input power. Now, all we have to do is get our output power and we divide that by efficiency, which is 0.936, because it's 93.6%, and we get input equals, so divided by 0.936, and we get 23.91 kilowatts. And if we look at our model answers, once again, it is output divided by efficiency, so 22380 divided by 0.936 equals our 23.91 kilowatts. Now, moving on to question C. Question C, calculate the output power required to drive the full load torque of 142.63 Newton meters. So we are given our Newton meters, 142.63 for what the load requires, and 114.40 RPM. So we have P out, so for P external equals, and we have 2 pi T n over 60 equals 2 pi T is our torque, so that is our 142.63 times by our RPM, which is 1440 over 60. P external equals 2 times pi, where's pi in this one? There. 2 times pi times 142.63 times by 1440 equals, and then divide by 60, and we get so we get 21508 watts, which is equals our 21.5 kilowatts. Now, our question is, for I, calculate the motor output power required to drive the full load. So that is what's required to drive the full load is 21.5 kilowatts. Can the motor drive the full load torque of 142 Newton meters? State the reason to support the answer. So the output is 22.38 kilowatts from the motor, and the required is 21.5. So 22.38 minus 21.5 equals, so 21. And we get 0.88. So kilowatts. So we have in excess 0.88 kilowatts of power to get it to do what we want. Now, next question, calculate the line current of the motor. So all we need is our input power, which we have, and we need our voltage. and we need our power factor. So we have our input power is our 23.91. 23910 watts, and equals √3 times by our V line. Our V line, if we check back at our question, just to show you, it shows us 415 volts. So √3 times by V line, which is our 415 volts, times by our I line, times by our cos theta. Now our cos theta, if we look back at our book again, is 0.87. Now we divide both sides by what we're trying to get rid of. So square root of 3 times by 415 times by 0.87. Put it on the other side, √3 times by 415 times by 0.87. √3's cancel, the 415's cancel, the 0.87's cancel. So we end up with I line equals, from here, our 23910 over our √3 times 415 times 0.87. So now putting that into our calculator, so once again it's 23910 divided by, and then we'll have to put this in brackets, so I'll type it this way, square root of 3, so square root of 3 times by 415 times by 0.87, close bracket, equals, and we get 38.234 amps. And if we look at our model answer, it's 38.24 amps. So subtle difference, and that's more to do with rounding once again. Then we go to question E, state the current rating and type of the HRC fuses that are installed to protect the final subcircuit. We don't have a 38 or 39, so we would go for a 40 amp HRC, and then it's mostly going to be general or GM.